Hello everyone, I am Srichandra Seripuram and today I am going to give a presentation on evolution of display technology. The development of display, on which we spend an inordinate amount of time every day, is a product of long line of innovations. Much like the human eye, the final product, that is the display, is a fruit of very long line of incremental changes. There were enormous leaps forward also, but most of them were tiny improvements on existing and proven technology. But all these were vital for the modern display. In this presentation, we'll explore some of the major steps and people involved in the development of modern displays. So this is the overview of the presentation. So these are the major discoveries and inventions uh, which were done in the field of display technology. We'll go through them one by one. So first is a mechanical scan television. Mechanical television or the mechanical scan television is a system that relies on a mechanical scanning device such as a rotating disc with holes in it to scan the scene and generate the video signal, and a similar mechanical device at the receiver to display the picture. So here in the picture on the right hand side, we can see there is a rotating disc, and the receiver can see the picture through a hole through a hole in a disc. So a Nipkow disc, also known as scanning disc, is a mechanical rotating image scanning device patented in 1885 by Paul Gottlieb Nipkow. This scanning device was a fundamental component in the mechanical television. So, as in the picture in the right, we can see there is a disc. So, this is generally a Nipkow disc. So, it was discovered by Paul Nipkow. So, mechanical scanning methods were used in the earliest experimental televisions in the 1920s and 1930s. One of the first experimental wireless television transmissions was done by John Logie Baird on October 2, 1925 in London. So, Bayard's system used the Nipkow disc for both scanning the image and displaying it. A brightly illuminated subject was placed in front of the spinning Nipkow disc set with lenses which swept images across a static photo detector. The signal from the photo detector was then transmitted by AM waves to a receiver unit where the video signal was applied to a neon light behind a second Nipkow disc whose rotating is synchronized with the first one on the transmitter side. The brightness of the neon lamp was varied in proportion to the brightness of each spot on the image. As each hole in the pass, as each hole in the disc passed by, one scan line of the image was reproduced. Here on the bottom right, we can see like the scan lines being produced by the Bayard's television. So the image quality was not that great, and the photo detectors needed brightly illuminated subjects in order to produce the image. So the world's first public television station, started in Berlin in 1935, was named after Nipkow, the spiritual father of the core element of the first generation of television technology. The advancement of vacuum tube electronic television marked the beginning of the end for mechanical systems as a dominant form of television. They were still used to produce small images. So moving on to cathode ray tube or CRT. So most of us remember these big and bulky monitors that were on every computer desk in the 90s and 2000s. Uh, we also saw the TV in our living room in our childhood. So these were called cathode ray tubes or CRTs and were the earliest forms of electronic displays. This tech was first demonstrated in 1897 and was invented by Carl Ferdinand Braun. Braun was a Nobel Prize winning physicist and inventor. He invented the cathode ray tube, which is a vacuum tube that produces images when its phosphorescent screen is struck by electronic beams. So on the picture on the right, we can see John Logie Baird and the cathode ray tube which he invented on the bottom right. So it has a fluorescent screen which uh, which illuminates when electrons hit the screen. So initially they were used in oscilloscopes, but They found their way into TV applications and finally computers. So in 1907, Russian scientist Boris Rosing used a CRT to transmit crude geometrical patterns onto a television screen. This technology was later further developed and was first commercialized in 1930. The first commercially available cathode ray TV was produced in 1934 by the Telefunken company in Germany, and it actually costed around $8,000 in today's money. So that was very expensive at that time. But after World War II, the TVs would hit the mainstream. The first commercial color CRT was produced in 1954 by the RCA researchers. The reason CRT TVs were so heavy and bulky was that they consisted of an electron gun. The way the CRT works is that uh, this electron gun would fire electrons into an array of millions of tiny blue and green and red phosphor coated dots. The beam would fire horizontally row by row, and when the tiny phosphor dots were hit by the beam, they would glow. So when you do this rapidly enough, you can form the illusion of a moving image. Despite being inefficient, large, and full of hazardous waste materials like lead and phosphorus, CRT screens pretty much own the 20th century as a display of choice. It was a dominant form of display for many devices until it was surpassed by LCD, plasma, and OLED. So moving on, so Solari board or flip-flap disc displays. So this was invented in the 1950s. Uh, they were once a common sight in most of the public transport stations and airports. Uh, these are now mostly replaced by digital monitors, but it can be still found in some places around the world. So these were electromechanical display devices capable of displaying alphanumerical text, and graphics as needed. Each character position was printed on one or more flaps that were rotated to form a concise message. Sorry. Advantages to these displays include high visibility and wide viewing angle in most lighting conditions. So that is the reason they were put in railway stations and transport systems. So and they needed very low consumption when a display was static, since nothing was uh, nothing was used to change, and the distinct metallic flapping sound draw the attention of the people when the information was updated. So yeah, this was the major reason they were used in transport systems. So the sight and especially the sound of them is still fondly remembered by anyone uh, who had the pleasure of experiencing them in the childhood. Yeah, and the next is the vacuum fluorescent display, or the VFD. It was once commonly used in most consumer electronics equipment, such as the microwave ovens, calculators, and video cassette recorders. So the VFD operates on the principle of cathodoluminescence, which is roughly similar to cathode ray tube, but operating at much lower voltages. The very first VFD was a single indication display introduced by Philips in 1959. The first multi-segment VFD was a 1967 Japanese single-digit 7-segment device. These displays became common on calculators and other consumer electronic devices. In the late 1980s, hundreds of millions of units were made yearly. Since the late 1990s, backlit color active matrix LCD displays have been able to cheaply reproduce arbitrary images in any color, which is a marked advantage over fixed character VFDs. So this is one of the main reasons for the decline in popularity of VFDs. Many other iterations of the technology would appear over the following decades, and it can be still found today, although it has been replaced by LEDs and LCDs, which have much lower power requirements. Many low-cost DVD players continue to feature VFDs. Moving on, we have the monochrome plasma display. So this was a very big step forward in the history of displays. Although the principle behind this tech was first described in 1930s by an Hungarian engineer, Kalman Tihany, it was until the 1960s that the first practical example was developed. So the first monochrome plasma display was developed by the University of Illinois, uh, Donald Bitzer and H. Gene Slaughter, and a graduate student, Robert Wilson, for the Plato computer system. Uh, it provided a rather garish orange monochrome color and became very popular in the 1970s. So here in the picture on the right, we can see the garish orange monochrome color in both of the pictures. So this tech also had some popularity in the 1980s when IBM introduced a 48 centimeter orange and black display. So by the end of the decade, orange monochrome plasma displays were used in a high number of high-end portable computers such as the Compact Portable 386 and the IBM P75. So here on the bottom right, we can see the picture of IBM P75. So it was pretty bulky actually. So the advantages of plasma displays include better contrast ratio, good viewability angle, less motion blur than LCDs that were available of that at that time. So due to heavy competition from monochrome LCDs used in the laptops of the era and the high cost of plasma display technology, in 1987, IBM planned to shut down its factory in the upstate New York, which was the largest plasma plant in the world. Dr. Larry F. Weber, uh, a scientist at the University of Illinois, ECE PhD in plasma display research, and staff scientist working at CERL, which was the home of Plato System, co-founded a startup company called Plasma Co. with Stephen Globus, and also James Kehoe, who was the IBM plant manager and bought the plant from IBM for 50,000 US dollars. Weber stayed in Illinois as CTO of Plasma Co. until 1990, but then moved to upstate New York to work on site in the plant. So moving on, we have the electroluminescent displays or ELDs. Uh, British radio researcher Henry Joseph Round discovered the effect of electroluminescence in 1907. But electroluminescent displays first appeared in the 1970s. So these were a type of flat panel display created by sandwiching a layer of electroluminescent material such as gallium arsenide between two layers of conductors. As current flowed between through the material, the layer of luminescent material emitted radiation in the form of visible light. ELDs are less common than other types of monitor display, but can be found in industrial, instrumentation, and transportation applications. One of the main features of an electroluminescent display is that it provides a wide viewing angle as well as a clear and sharp image, which makes them suitable for the above applications. Uh, the next major discovery which led to the modern displays is a twisted pneumatic effect, which caused the birth of LCDs. So, liquid crystals were accidentally discovered in 1888 by Austrian botanist Friedrich Riesner while he was studying cholesterol benzoate in carrots. Uh, the twisted pneumatic effect was first noticed by French physicist Charles Victor Morgan in 1911. He discovered that an electric field can be used to align special liquid crystal molecules between two states. Normally, if two polarizers are aligned at right angles, light will not flow through them. But it was observed when liquid crystal was sandwiched between the two polarizers and then light was shown from one side. He noticed that the light actually passed through. He found that the liquid crystals under twisted state, that is when no electric field is applied, polarize the light by 90 degrees. So when an electric field is applied across the crystal, the liquid crystal molecules align and do not polarize the light passing through it. So light passing through can be controlled using a small voltage. Uh, Wolfgang Helfrich, a physicist working for RCA in 1967, had the idea to use this phenomena to make electronic display. The RCA Corporation, this RCA Corporation, whom he was working under, showed very little interest in this project. So Wolfgang left and joined the Hoffmann Laroche lab in Switzerland, where he teamed up with Martin Schadt, a solid-state physicist. He managed to build some working samples in 1970. Also at this time, Brown, Boveri and C, short for BBC, was also working with the devices as a part of prior joint medical research agreement with the Hoffman Loresh lab. BBC demonstrated their work to a physicist from the US who was associated with James Ferguson, who was an expert in liquid crystals at the Westinghouse Research Laboratories. So James Ferguson was also working on the twisted pneumatic displays. So when the news of the demonstration by the BBC to US physicists reached the Hoffman Loresh lab, Helfrich and Schadt of the Laroche lab immediately pushed for a patent, which was filed on 4 December 1970. In order to demonstrate the feasibility of the new effect for displays, Schadt fabricated a 4-digit display panel in 1972. So, seeing this, Ferguson also published a similar patent in the US uh, on 9th February 1971. So, this was 2 months after the Swiss patent was filed, and so this led to a 3-year legal confrontation that was settled out of court. In the end, all the parties received a share of what became many millions of dollars in royalties. Yeah. So in 1972, the first wristwatch featuring the technology was released. It was called the Gruen Teletime. So here in the picture on the right, we can see an advertisement of the Gruen Teletime, which actually is pretty interesting. So they advertise that what the television did to radio, Teletime is going to do to the watch. Mm. So unlike other displays which could require 40 volts or more to run, this twisted pneumatic display uh, method used hardly any power and made them perfect for portable devices like pocket calculator or wristwatch, and as we'll soon see, modern LCDs. Super twisted pneumatic effect (STN) brings LCD monitors even closer. So super twisted pneumatic effect, or STN for short, was first discovered at the Brown Boveri Research Center in Switzerland in 1983. So standard twisted pneumatic LCDs have a 90 degrees twisted structure of the molecules, uh, which have a unfavorable contrast versus voltage characteristic for passive matrix addressing. Exchange displays with the molecules twisted from 180 degrees to 270 degrees have superior characteristics and can be used for passive matrix addressing. So we'll soon see what is passive matrix addressing. So HDN LCDs require less power and are less expensive to manufacture than TFT LCDs, which we'll again see later, which was another type of popular LCD. Uh, yeah, HDN displays typically suffer from low image quality and slower response time than TFT displays. However, STN LCDs can be made purely reflective for viewing under direct sunlight. STN displays were used in some inexpensive mobile devices and informational screens of some digital products. They began to be used in early portable computers in the 1990s, like the Amstrad PPC 512 and PPC 640, and also in the Nintendo's Game Boy. A later development uh, called color super twisted pneumatic or CSTN was developed in the 1990s. These were like a color form of the electronic display screens originally developed by Sharp Electronics. So these color super twisted pneumatic LCDs began to appear in early mobile phones like the Nokia 3510i. So here in the picture on the top right, we have the picture of Nokia 351i, which use the STN LCDs. And on the bottom right, we have the voltage versus transmission characteristic of STN and the standard TN. Yeah. So to match with the TFT and other display technology, several advancement of STN were made. Some of these are double layer STN, dual scan STN or the DSTN, uh, FR STN or the fast response STN, FSTN, which is the film compensated STN or filtered STN, and finally the CC STN, which is the color coded super twisted pneumatic. So with the development of TFTs and the introduction of OLEDs, the usage of STN LCDs has reduced a lot. So continuing from the monochrome plasma display, so we move on to the full color plasma display. So in 1992, Fujitsu introduced the world's first 21-inch full color display. It was based on technology created at the University of Illinois and the NHK Science and Technology Research Laboratories. In 1994, Weber, who we saw previously in the monochrome plasma display, demonstrated a color plasma display at an industry convention in San Jose. Panasonic Corporation began a joint development project with Plasma Co., which was the startup created by Weber, uh, which led in 1996 to a purchase of Plasma Co. And its color AC technology and its American factory for $26 million US. The year of 1995 saw the introduction of the world's first 107 centimeter plasma display thanks to Fujitsu. It actually had an impressive 852 times 480 resolution, which was pretty amazing at that time. Uh, 2 years later, Philips introduced the first large commercially available flat panel TV using the Fujitsu panels. Uh, but they were exceedingly expensive at this time, with the average price tag somewhere in the region of $15,000. Other companies like Pioneer soon began to make and release their own versions. In the year 2000, the first 60-inch plasma display was developed by Plasma Co. In late 2006, analysts noted that LCDs had overtaken plasmas, particularly in the 40-inch and above segment, where plasma had previously gained a major market share. Until the early 2000s, plasma displays were the most popular choice for high definition TV, flat panel display, as they had many benefits over LCDs. It was believed that LCDs were only suited to smaller size televisions, but however, improvements in VLSI fabrication narrowed the technological gap. The increased size, lower weight, falling prices, and often lower electrical power consumption of LCDs made them competitive with the plasma television sets at that time. Uh, by the late 2013, Panasonic announced that they would stop producing plasma TVs from March 2014 onwards. Again, in 2014, LG and Samsung discontinued plasma TV production as well, effectively killing the technology, which was probably because of lowering demand. So here on the top right, we can see the schematic of PDP, which is a plasma display. So it consisted of display electrode. It consisted of cells which have red, green, and blue colors, which were produced by gases inside them, and there were electrodes which would apply some voltage in the on the gas, and which would produce the light accordingly. So on the bottom right, uh, we have the first 60-inch plasma display uh, produced by Fujitsu. And moving on, we have the thin film transistor LCDs, which you saw earlier, which is the TFT LCDs. So it is the variant of LCD that uses thin film transistor technology to improve image qualities such as addressability and contrast. In February 1957, John Wallmark of RCA filed a patent for thin film MOSFET. Paul K. Weimer, also of RCA, implemented Wallmark's ideas and developed the thin film transistor in 1962, which was a type of MOSFET distinct from the standard bulk MOSFET. So it was made from thin films of cadmium selenide and cadmium sulfide. The idea of TFT based liquid crystal display was conceived by Bernard Lechner of RCA Laboratories in 1968. Uh, in 1971, Lechner, along with a few other researchers, demonstrated a 2 by 18 matrix display driven by a hybrid circuit in LCDs. Uh, in 1973, T. Peter Brody, J. A. Assars, and G. D. Dixon at Westinghouse Research Laboratories, which we saw earlier in plasma display, developed a cadmium selenide TFT, which they used to demonstrate the first cadmium selenide thin film transistor liquid display, which is a TFT LED LCD. So as described earlier, LCD screens work by using the twisted pneumatic effect, and modern screens still use this technology, but on a wider scale. And again, when you put millions of these together to form the pixels, this is how we get our display technology. So how do we control each pixel if we have millions of pixels on the screen? So this is a question which we get. So it turns out that there's a tiny transparent grid of wires with each pixel having three transistor switches. So we'll get the question again, why three? This is because within each pixel there are typically three subpixels, which is the red, green, and blue. So as you see in the bottom right picture, we can see the transistors for each red, blue, and green uh, pixels. So this is a picture of TN display under a microscope, and yeah, so the transistor will so these tiny transistors control the level of brightness of each subpixel by using a tiny voltage to represent a single color as per the instructions of graphics driver of our computer. So the transistor will vary the brightness of green, red, and blue subpixels separately. Uh, and when we combine millions of these subpixels together, we get our image. One fascinating thing is that the driver can control only one row at a time. Uh, but the speed at which these rows are updated is so rapid that our eyes can perceive it as a single complete image. So this technique is called the active matrix display and was first introduced by the Westinghouse Corporation in 1974. By 2013, all modern high-resolution and high-quality electronic visual displays uh, used TFT-based active matrix display. They were used in applications including television sets, computer monitors, mobile phones, handheld devices, uh, personal digital assistants, navigation systems, and dashboards in automobiles. Uh, Moving on, we have the multi-touch display. So this is not exactly a display technology, but it's the interface between the screen and the user. So when we touch and navigate our phone, uh, we use two fingers to pinch and zoom or perform gestures. But it always wasn't this way. So this technology is called the capacitive multi-touch. The origins of multi-touch began at CERN and a number of US and Canadian universities in the 1970s. CERN began using multi-touch screen as early as 1976 for the controls of the superproton synchrotron. So as we can see in the picture on the top right, we have the prototype of the capacitance multi-touch screens developed at CERN. So multi-touch technology is capacitive as opposed to resistive, which was a kind of technology in which you had to use force in order to register a touch. To register a touch. Like for example, think of ATM screens. Early PDS, which is the personal digital assistants like the Apple Newton or Windows mobile devices, used this kind of technology, making them clunky to use. And this was the main reason why most of the public was skeptical of touchscreen devices at the time of the iPhone's release. Capacitive touch, on the other hand, uses the human finger as an electrical conductor, which causes an electrostatic change in the screen surface. This change can be measured, and it results in more accuracy than resistive methods. A capacitive touchscreen typically consists of capacitive touch sensor, application specific integrated circuit, which is the ASIC controller, and digital signal processor DSP, fabricated from CMOS technology. Uh, like between 1999 and 2005, the company Fingerworks developed multi-touch devices mainly for those with wrist injuries and a disabled. So this is an interesting story. One day in 2002, an Apple engineer who had broken her wrist brought one of these devices into the office to work. So other Apple engineers were fascinated, and Apple later ended up buying the Fingerworks company. So this key technology eventually became used in the iPhone in 2007. Other technologies used to realize multi-touch display are the electromagnetic guidance technology, optical touchscreen technology, and the surface acoustic wave technology. So here we can see the example of optical touchscreen technology. So it uses light to detect the touch of our finger on the screen. Moving on, we have the organic light emitting diode or the OLEDs. So OLEDs uh, is a light emitting diode in which the emissive electroluminescent layer is a film of organic compound that emits light in response to an electric current. So this organic layer is situated between two electrodes. Uh, and in general, at least one of these electrodes is transparent to pass light. An OLED display can be driven with a passive matrix, then which is then called PMO LED, or active matrix, which is then called the AMOLED or AMOLED control scheme. In the PMO LED scheme, each row and line in a display is controlled sequentially one by one, whereas AMOLED control uses TFT backplane to directly access and switch each individual pixel on or off, which allows for higher resolution and larger display sizes. So this is the basic difference between passive matrix and active matrix control schemes. Unlike LCDs, OLED displays doesn't need a backlit because they themselves emit light in response to current. This way, OLED screen can achieve a higher contrast ratio than LCD. Uh, Andre Bernanos and co-workers at the Nancy University in France made the first observation of the electroluminescence in organic materials in the early 1950s. In 1960, Martin Pope and some of his co-workers at New York University developed ohmic dark injecting electrode contacts to organic crystals. These contacts are the basis of charge injection in all modern OLED devices. Pope's group also first observed DC electroluminescence under vacuum on a single pure crystal of anthracene. The first polymer LED, PLED, to be created was by Roger Patridge at the National Physical Laboratory in the United Kingdom. The light generated was readily visible in normal lighting conditions, though, but the polymer used had two limitations: low conductivity and the difficulty to inject electrons. His contribution has often been overlooked due to secrecy NPL, which the National Physical Laboratory imposed on this project. So it was patented in 1974 by the government's Department for Industry, tried and failed to find industrial collaborators to fund further development. As a result, publication regarding the polymer LEDs was delayed until 1983. Chemists Ching Wang Tang and Stephen Van Slyke at the Eastman Kodak built the first practical OLED device in 1987. They made a device such that the light emission occurred in the middle of the organic layer, which resulted in reduction in operating voltage and improvements in efficiency. Uh, White OLEDs, pioneered by J. Kido at Yamagata University, Japan in 1995, achieved the commercialization of OLED backlit displays and lighting. Uh, Manufacturing of small molecule OLEDs was started in 1997 by Pioneer Corporation, followed by TDK in 2001, and Samsung NEC Mobile Display (SNMD), which later became one of the world's largest OLED display manufacturers in 2002. The Sony XCL1, released in 2007, was the first OLED television. So here on the picture on the bottom right, we can see the Sony XL1, which was the first OLED TV. In 5th December 2017, uh, JOLED, the successor of Sony and Panasonic's printable OLED business units, began the world's first commercial shipment of inkjet printed OLED panels. A major area of research is the development of is the further development of white OLED devices uh, for solid state lighting applications, which is the tube lights and light bulbs. So Research is also being carried out in increasing the lifetime efficiency of OLEDs and also for creating foldable LEDs, which is the FOLEDs, FOLEDs. Yeah, so here in the picture in the top right, we can see the magnified image of the AMOLED screen uh, on the Google Nexus 1 smartphone. So here we can clearly see the red, blue, and green subpixels as well. And all these are controlled by using a TFT, uh, using transistors. So these are some of the major events in history that led us to the development of display technology to this scale. Without any one of these steps, it is unlikely that modern full color screens would ever have been developed. Today's display market offers an abundance of choices, each with their own advantages and disadvantages. The choice of technology greatly depends on the intended applications, like whether it is home entertainment, portable electronics, or industrial purpose. We saw that CRTs, which initially monopolized the display industry for about 50 years, uh, were completely replaced by LCD technology. The LCD technology dominated the market for about 15 to 20 years before starting to get replaced by OLEDs. So currently OLEDs hold the largest market share in the display market. In other display applications, technology such as the plasma displays, uh, FEDs, which is the field emission displays, and electronic paper are also competing for the market share. Uh, Display technology is the most effective way to communicate information. As researchers continuously create innovative ideas, display technologies are becoming more and more sophisticated. Some of the next generation display technologies include the OLEDs, which is organic light emitting transistors, the micro LED, uh, FEDs, which is field emission display, the QD LEDs, which is the quantum dot LEDs, and ELQ LEDs and AMQ LED, which are the electroluminescent quantum dot LEDs and the active matrix quantum dot LEDs. So these next generation displays will probably be lighter, thinner, flexible, more adaptable, power efficient, and also conform to the changing needs of the society. So here in the picture on the right, we can see uh, the timeline of how the display technologies evolved. Uh, we still don't know what's gonna be in the future, but we just have to wait and watch. Thank you.